Welcome back. In this video, we're going to talk about the general form for the equation of a plane, and we'll use the intuition that we built from equations for lines in R2 in our last videos to get started. Let's go back to the conclusion of the last video, which was when we're discussing lines in R2, we have two different ways to do so. The explicit function equation for lines in R2 starts with a point on the line and then a slope of the line, which we look at as a rise over a run. Each slope corresponds with a unique direction vector, which comes from the parametric equation for the line. And we can think about in the explicit representation, the line is the set of all points starting from point P naught and then going in the direction of V, or a long slope M. However, we also saw that we could implicitly define the line by encoding the normal vector to the line, or the vector perpendicular to V, and looking at the line as the set of all points that create vectors orthogonal to n. In other words, if we looked at the set of all general points, what we might call P of x, y, and we created a vector x from P naught to P, then the line is the set of all vectors that are orthogonal to the unique normal vector. And the normal vector, is not unique, but the direction associated with the normal vector is unique. Each individual direction vector has one and only one normal direction. Once we have this in mind, we can think about the analog in R3. Just like a single vector, direction vector v, creates a line, we might say that on a plane is created when we have a point P naught on the plane, and then we have two direction vectors that are non-collinear. And non-collinear basically means that one cannot be written as a scalar multiple of the other. So the angle between these two vectors is definitely not 0 or 180. It's somewhere in between there. In this case, we would say that if you looked at a plane in this definition, we could write it as a multiple input vector valued function where you're really looking at some affine transformation. Don't worry about the words I'm using. Basically, you have the point that you start at and then any linear combination of u and v. In linear algebra, you'll hear this called the span of u and v, any linear combination. Don't have to worry about that. The point, though, is that in this explicit representation, notice there's a lot going on. This requires a lot of details. However, we might see an analog between what's going on in the implicit representation of a line with what could go on in an implicit representation of a plane. In particular, if we think about the plane as the set of all possible combinations of u and v going through the point P, we could also see that such a plane has a unique normal direction. Notice it doesn't have a unique normal vector because there's infinite number of normal vectors in this direction. But the point is that we could think about the plane as every single point here that creates vectors orthogonal to n. And I might just remind us, in kind of hard to draw this, but this vector would be orthogonal to both of those. Oh my God, do you see something? If I gave you two vectors and I asked you to find the one orthogonal, do you know a way to do that? Yeah, and so in this intuition, what we see is that this whole idea of implicitly encoding a line is actually a really, really powerful way of thinking about planes. So instead of thinking about planes as the span of two vectors in different directions, we can uniquely encode the plane by the normal direction of that plane. And that's what I'm going to write here. We might uniquely determine a plane by a point on the plane. So we have some initial point that's definitely on our plane. And in addition, a unique orthogonal direction. This orthogonal direction, out of this orthogonal direction, we would choose a single non-zero normal vector n to define the plane. And I like to kind of give intuition behind this diagram. So this is my favorite diagram to think about the equation of a plane. So perhaps we have some plane oriented in space. You're going to have to pretend that my drawing is sufficient and that you can understand what the heck I'm doing. So you have some plane in R3, and then the whole idea of a plane is that it's a collection of points. So perhaps you call this the original point that for sure you know is on the plane, x, y, z naught. And then you have some general point on your plane, which we call x, y, z. We'll call the vector connecting our specific point to any point, we'll call that vector x. When we define this plane, we'll think about collecting all points p of x, y, z such that the corresponding vector x from p naught to p is orthogonal to n, where n is any vector pointing in the normal direction. So in this case, in order to do this, we want to have a specific point on the plane p naught, which has three components, or coordinates, x naught, y naught, z naught. And this is a point, not a vector. And then we have what we call a normal vector, and that's the thing orthogonal to any vector in the plane, and we'll call that n. And in this case, we would write n as three components a, b, c. And then we would have a general point, any point, general point on the plane, p of x, y, z. And then we would say that the vector x is the vector from p naught into p, and we want to choose p such that vector x is orthogonal to n. That's kind of the general diagram there. And the whole claim that we just made was, when we think about that diagram, given a point p naught on the plane and a normal vector to the plane, which encodes a direction, the plane itself is the collection of all points such that the vector x from p naught to p is orthogonal to n. Well, remember, what does it mean to be orthogonal to n? It means that if you took n dotted with x, when are two vectors orthogonal? When their dot product is 0. And again, we remember that x was equal to the vector connecting p naught to p, which of course would be x minus x naught, y minus y naught, z minus z naught as a vector. Oh, rookie move, didn't give myself enough space. When we look at this thing, we would have this as a, b, c, dotted with x minus x naught, y minus y naught, z minus z naught equals 0. I guess I would actually fit one more in. I actually really like this description of the plane, where I think about the plane itself as all points that create vectors orthogonal to the normal vector. And I like to think about this as like the dot product equation for the plane. So here I like to think about this as like the dot product equation for the plane, and then we are constructing, or we're searching for all these points p. N is given, p naught is given, it's the p that we want to fill in. And what's really nice about this is, if you remember this general structure, all the rest of the work is done for you just by doing a dot product. So we can expand this thing. Here we take the dot product, which is to multiply the components and add the products. And then we have C outside of Z minus Z naught equal to 0. And of course we can distribute. This would be AX plus BY plus CZ equal to D. And in this case, D comes from distributing the A, the B, and the C onto each of the specific coordinates, x naught, y naught, z naught, and bringing it over to the other side. Well, here this would be negative. When I bring it over, it would be positive. The same thing's true with the B, so this would be B, y naught, and then also C, z naught. These are two different scalar equations for the plane, and notice that both of these are implicit relationships, which we'll highlight in a second. So I like to think about these as what I would call scalar equations for a plane, and these are implicit relationships. And the moment we know that they're implicit relations, that means that when we were going to graph them in Mathematica, we would probably use contour plot 3D, since they're in 3D. Now that we've seen this particular definition, this is the dot product version. These are both scalar equations for plane. One of them directly references the point. The other one implicitly references the point. Each of them, the output variable z, is not isolated in terms of x and y, which is why we call these implicit relations. Now that we have this, let's go on to solve some problems and look at how to use this in practice. I'll see you in the next video.